continue with the chapter equipotential surface. Equipotential surface. Equipotential surface means the surface which has same electric potential on all points. Same electric potential on all points. So this surface is called equipotential surface. So one surface will be there. On all the points of the surface, the electric potential value will be same. Okay, that is called as equipotential surface. For example, I am taking one sphere. Okay, sphere. Okay, so the center of the sphere, I am marking it as O. This is the surface of the sphere. Okay, so I am taking this point A. This point will have one electric potential value. Okay, V. And I am taking another point B. This will have the electric potential value V. Okay, similarly C, D, E, F, like that many points I am taking on the surface. So all the points on the surface will have same electric potential. Then this surface we can say that as equipotential surface. So if the surface is having same electric potential on all the points, then the surface is called as equipotential surface. Okay. Now suppose I am drawing one small sphere. Okay. On top of that I am drawing another sphere, and then I am drawing another sphere. So this surface is having some 5 points like this. Okay, so in this surface all the points will be having same potential. Let us assume that the potential is V1. Okay, now the second sphere is having many points. Okay, this surface will be having electric potential V2. The third surface also will be having many points. So this will have electric potential V3. So V1, V2, V3 will not be equal. Okay, because this is different surface, this is different surface. Okay, so V1 will not be equal to V2, it will not be equal to V3. Okay, so the points on this surface and the points on this surface will not have same electric potential. Okay, so only the points on the same surface will have same electric potential. Then this surface is called equipotential surface. So this is one equipotential surface, this is one equipotential surface, this is one equipotential surface. But all the three equipotential surfaces will not have same potential. Okay, but all the points in the surface will have same potential. Okay, right on. So this is for the spherical surface. Suppose if we are having a uniform electric field. Uniform electric field means we will be representing it like this. Okay. So for the uniform electric field, how the equipotential surface will be? For the uniform electric field E vector, the equipotential surface will be in the form of a plane sheet. Okay, it will be in the form of a plane sheet, and the sheet will be perpendicular to this electric field. Okay, the sheet will be perpendicular to the electric field. So for the equipotential, so for the uniform electric field, the equipotential surface will be in the form of the plane sheet and it will be perpendicular to the electric field. Okay. So next, what are the properties of equipotential surface? Properties of equipotential surface. Okay, suppose I am taking a surface like this. There is a point A and there is a point B. Okay, in an equipotential surface, there is a point A and there is a point B. Okay, suppose if I want to move the charge Q, I am going to move the charge Q from point A to point B. I am going to move the charge from point A to point B. So for moving the charge, what I will do? I will do some work. So the work done W will be equal to charge into, okay, charge into, from which point to which point we are moving? We are moving from point A to point B. So this point A will have the potential VA. Suppose I will take these two equipotential surfaces. Okay, in this surface I am taking point A, in this surface I am taking point B. So I am going to move this charge from point A to point B. Okay, so the work done is equal to W is equal to the charge Q into this point B will be having another equipotential, another potential VB. The point A will be having the potential VA. So work done is equal to Q into VB minus VA. VB minus VA. So this condition we will use when there are two equipotential surfaces. So I am moving from A point to B point. A point is in another surface, B point is in another surface. Suppose A and B are on the same surface. A and B are on the same surface means this potential and this potential will be same. So if A and B are on the same surface, if they are on the same surface, then the VA value will be equal to VB value. Okay, at that time the work done VA value, VB value will be equal. So minus pannana we will get 0. So work done will be 0 if we move on the same surface. But if we move on the different surface, it will not be equal to 0. Okay, take that. Relation between electric field and electric potential. Relation between electric field and electric potential. Okay, so this formula we will be using for problems. Okay, so I am going to consider a positive charge. Okay, I am going to consider a positive charge Q. Okay, so this point, the positive charge Q is placed at the origin. Origin means what? It is placed in the center. Okay, now I am going to move this charge. I am going to move this charge. So I am going to move this charge through a small distance. This distance I am going to take it as dx. Okay, so I am going to move the charge Q through a distance of dx. Okay, then so for moving this charge I am going to do some work. So what will be the work? So for moving the small distance, I will be doing small work. dW means small work. dx means small distance. So for moving the small distance, I will be doing a small work. Okay. So dW is equal to, okay, I am going to move the charge through the distance dx. Okay, where the charge is placed? The charge is placed in the electric field. So I will get E into dx. So the charge is in electric field and I am going to move a small distance dx. So work done is equal to E into dx. So I am going to do this work against the electric field. Okay, against the electric field. So against the electric field means I have to put minus sign. So dW is equal to minus E into dx. So what is the meaning of this negative sign? It means that work is done against the electric field. Okay, against the electric field. Okay, now the work done is equal to potential difference. dW is equal to dV. Why we are writing work done is equal to potential difference? Only if we have the potential we can do the work. Okay, another work done is equal to potential difference. So dW is equal to minus E dx. Instead of dW, I can substitute dV. So what I will get? dV is equal to minus E into dx. Okay. So I want expression for E. So what will be E? E is equal to minus dV by dx. Minus dV by dx. So this is along the x-axis alone. If I move it along x-axis, okay, one dimension. Suppose if I am moving it in a three-dimensional way, three-dimension now all the three axes will come. Then what will be the electric field? Electric field is equal to minus dou V. Dou means what? Partial differentiation. D means complete differentiation. Okay. Only one axis is there, so complete differentiation. If there are three axes, x-axis little bit we will differentiate, y-axis little differentiation and z-axis differentiation. So dou V by dou x plus dou V by dou y plus dou V by dou z. Okay, so if it is moving in a three-dimensional path, so this is moving in a straight line, one dimension. Okay, so this is the difference between relation between electric field and electric potential. Okay, so take up. First point, E is minus dV by dx. Minus means what? This we are doing the potential against the electric field. Against the electric field means what will be there? When the potential is less, okay, then in which point the potential is less, at that point the electric field value will be maximum. Okay, it is like inversely proportional. Okay, so read the point in the book. Electric field will be in the direction in which the potential energy decreases the steepest. So in which direction the potential is very low, in that direction the electric field will be there. Okay, so next one, how we can tell this? What is dV? D means the change in the potential. dx means what? The change in the distance. So change in potential per change in distance. Change in potential per change in distance, we can tell it as electric field, or we can tell that as the work done. So what is the definition for work done, or what is the definition for electric field? Abdina, it is the change in the electric potential per change in the distance. Okay, so read that point. The magnitude of the electric field. Its magnitude, not the magnitude of the electric field. It is given by the change in the magnitude of potential. Change in the potential. Okay. Per unit. Per unit means divided by. Divided by the displacement. Displacement means what? Change in the distance. Okay. Understood? Okay. Next. Heading. Electric potential due to potential energy due to the system of charges. Potential energy due to the collection of charges. So if there are many charges, how the potential energy will be? Okay, that is what we are going to see. Okay. First we will derive the general expression. What is the formula for electric potential? V is equal to 1 by 4 pi epsilon naught into Q by R. Into Q by R. Okay. So suppose if there are two charges Q1 and Q2. So electric potential for the Q1 charge, it will be 1 by 4 pi epsilon naught Q1 by R. Okay. Now I am going to bring this Q1 charge near this Q2 charge. I am going to bring the Q1 charge near the Q2 charge. So for bringing the charge, for moving the charge, I will be doing some work. So what will be the work done? So work done V is equal to, work done W is equal to, I am bringing it near Q2 into potential V. Okay. So work done will be equal to Q2 into V. So what is the V formula? 1 by 4 pi epsilon naught into Q1 by R into what? Q2. So 1 by 4 pi epsilon naught Q1 Q2 by R. When we can do the work? Only if we have energy we can do the work. So work done is equal to this one. Instead of that I can write energy is equal to this one. Why? Because only if I have energy I can do the work. So instead of writing in terms of work done, I can also write in terms of energy. So U means potential energy. So potential energy is equal to 1 by 4 pi epsilon naught Q1 Q2 by R. Okay, this is the general expression. Now, first one. I am going to take three conditions. First condition, my place is empty. My place is empty. From infinity position, I am going to bring the charge Q1. From infinity position, I am going to bring the charge Q1. So, I am going to bring the charge Q1. From where I am bringing the charge? From infinity position, I am going to bring the charge. Okay. So, for bringing the charge from infinity position, okay, we need not do any work. Okay, we need not do any work because there are no other charges. Only one charge is there. Okay, and the place is empty. So, in this case, no work is done. No work is done. Now, already I am having the charge Q1. Okay, now near this Q1 charge, I am going to bring Q2 charge. I am going to bring Q2 charge near this Q1 charge. Okay, so the distance between this Q1 and Q2, I am going to take it as R12. Okay, so for bringing Q1, I am not doing any work. But for bringing this Q2, I must do some work because already charge is there. Q1 charge is there. So I have to do the work against this force. Okay. So I am going to bring this Q2 charge. So I am going to do some work. So in this case, the work will be equal to, okay, 1 by 4 pi. What is the formula? 1 by 4 pi epsilon naught Q1 Q2 by R12. Okay, so I am bringing the first charge. Okay, so the potential energy U1. Okay, instead of W, I can write in terms of potential energy. U1 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. Okay, so for bringing Q1, I am not doing any work. For bringing Q2, this is the energy required to bring this Q2 charge. Now, I have Q1 and Q2. I am going to bring the charge Q3. Next, what charge I am going to bring? Q3 charge. Okay, so already I have Q1 and already I have Q2. What is the distance between them? R12. Okay, wow. Now I am going to bring another charge Q3. Okay, so Q3 I am bringing. Q3 when I am bringing, already what are the charges present in my place? Already Q1 is also present, Q2 also is present. So this also will have one effect on Q3. This also will have one effect on Q3. So the distance between Q1 Q3 I am taking it as R13. Q2 and Q3 I am taking it as R23. So what will be my potential energy here? U2. This is my second potential energy because I am bringing the second charge. Okay, so what will be the potential energy? 1 by 4 pi epsilon naught Q1 Q3
by R13
and this also will have one effect. Yes or no? So plus what I will get?
Q2
1 by 4 pi epsilon naught Q2 Q3 by R23. So can I take 1 by 4 pi epsilon naught outside? So U2 is equal to 1 by 4 pi epsilon naught Q1 Q3 by R13 plus Q2 Q3 by R23. Okay, this is my second potential energy. Okay, so for bringing the second charge, first I am bringing Q2, then I am bringing Q3. Okay, so first work is 0. Second energy is this one and third energy is this one. So what will be my total energy?
U1 plus U.
Total potential energy. Okay, total energy U will be equal to first energy is 0 plus second energy 1 by 4 pi epsilon naught Q1 Q2 by R12 plus what is the second energy? 1 by 4 pi epsilon naught Q1 Q3 by R13 plus Q2 Q3 by R23. So here I can take 1 by 4 pi epsilon naught outside. So U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. Okay, so this is my total potential energy due to the collection of charges. Again, if one more charge, if I bring Q4, okay, if I bring Q4 abdina, this distance, this distance, this distance I should take, and one more term will come here. Upper total பண்ணும்போது again one more term will come here. So like that it will go on. Okay, so copy that.